Alright, here's a Physics 2 type problem. Let me move my mic a little closer. Okay. So this is a Physics 2 type problem that was recommended in my Discord. So if you don't have Discord, you should join because it's awesome. Got a lot of people in there that like physics, and we all kind of just help each other out. So that link will be in the description if you're interested. And I decided to go through this problem because it's a very common problem that a lot of students will see in like a Physics 2 class. So I think it's worth taking the time and going through. Now, one thing that's interesting, and this is mostly speaking just to the person that asked it, is I think this is maybe a little bit of a translation, but the problem wants to know the force on Q4, and we're given all the charges. But it says calculate the vector of the electric interaction strength in the void what acts on the charge Q4. And somebody asked kind of to elaborate on that, and basically he says it means that the charges are not necessarily structured like this. They could be moved around. So I'm going to be very general with how I solve this, and then at the end I'll set it up for a problem that is structured like this. But I'm going to be very, or as detailed as I can be, in how I set this problem up. Okay, well, with all that out of the way, actually there's one more thing in the way. If you enjoy these type of videos, please like and subscribe. I'm trying to grow my channel, so I'd really appreciate it. Okay. So we're interested in, use I guess this color that stands out, Q4. We want to know the force on Q4. So it's always helpful whenever you're interested in forces to draw a FBD, free body diagram. And we'll do this of Q4 because that's the charge in question. And well, I guess we'll start with Q1. So Q1 is a different charge than Q4. So it's going to attract it. Force of 4 onto 1. Q2 is also a different charge, so it's going to attract it. So this will be F 2 on 4. And again, the third charge will also attract it. So this is F 4 3. Or however you want to denote it. Some people have different ways to denote it, but okay. So there's a free body diagram, and this free body diagram could change if you, for example, move this point charge up here, or this one goes down here, right? They could change a little bit. In this case, you would have a force going this way and then a force going that way. That could all be the case, but I just wanted to draw something out so that we have something to visualize here. Okay, so now Coulomb's law tells us that our force, our electrostatic force, is 1 over 4 pi epsilon naught, some constants, times, call it Qi, Qk, over r squared. So these two charges, one we would say is the test charge, the other is the source charge. Oops. So Q sub I, for example, it doesn't really matter because you're multiplying it, so the order that you multiply it in doesn't matter, it's commutative, but we'll just say Q sub I is the charge that's feeling the force, and Q sub K is the one that's actually causing the force. And R is just the distance between the two point charges. Okay, so if we want to find the sum of all forces, that's equal to 1 over 4 pi epsilon naught. And then we can start with the first one. Okay? We have the force that Q1 puts on Q4, pulls it upwards. So we'll just say Q1 times Q4 divided by the distance between them squared. So R14 is the distance between particle 1 and 4, or the point charge. Okay? Plus 1 over 4 pi epsilon naught times Q2 times Q4 over R24 squared. And I should be putting little unit vectors, R hat. Call it just R hat for now. Plus 1 over 4 pi epsilon naught times Q3 times Q4 all over that distance squared. Oops. So this is the most general way you could do it. But if you want to solve this, you need to know the distance between them. Okay? So what I would probably do is do essentially an example where we're using this structure. And if you're giving a different structure, hopefully you'd be able to then apply that to other problems. But this is a general structure. You could, for example, factor out a 1 over 4 pi epsilon naught. You'll notice that each term has a Q4. That's the charge feeling the force. You could factor that out. And you're left with the charge divided by the distance between them squared. I'll just pull an R hat out. And then what you would do is you would essentially just break that up if they have any components, but it depends on the problem. So this is kind of the part I wasn't super sure what they meant by. This is, I guess you could say, the most general expression you could have. But, I mean, I'm assuming there's some reason that we have these numbers that were given. So we can go ahead and solve that. So we have, and I believe, let me check the problem, where all the charges are the same. I'm looking on the Discord. Q1 equals 2Q equals Q3. But Q4 is different. Okay, so Q1 and Q2 and Q3 are the same. So we'll just say that Q1 equals 2Q equals Q3 equals big Q. And we'll just say Q4 is Q. So I can, since this is Q, this is Q, that's Q, big Q, we can factor that out. And really you're just left with, maybe this is a bit more general. Well, not any more general, but a little bit more hessed out. Okay. Now, what we want to do, and it kind of hurts that we change that. But now we're going to work through this example. So we have 1 over 4 pi epsilon naught little q times big Q. And the distance between 1 and 4, well, in this example, we can see that this is a right triangle, or this is the hypotenuse of 5. This is our 1, 4. And then this would be half of 3, so 1.5. So then our distance squared plus 1.5 squared equals 5 squared. 1.5 squared is 2.25. So our 1/4 squared equals 25 minus 2.25, and of course you don't really need to take the square root because we're interested in the square anyways. It's 22.75. Okay. And then I guess we can just put this in here. Oops. And then let's go ahead and get the direction right. So Q1 is pulling it up in the, we'll call it Y direction. We'll let up be Y, positive Y, the right be positive X. So this would be in the Y hat direction. 2 on 4 would be in the minus X hat direction. 1 over 1.5 squared X hat. And the third one would be also shifted to the right by that same amount. So this kind of makes sense because we have some symmetry in the problem. And these clearly cancel with one another. So you're left with just this term, whatever that ends up being when you plug in the values. But it's only in the Y hat, positive Y hat direction. So these two negative charges, Q2 and Q3, essentially cancel each other out, and the particle just accelerates upwards since it feels just that. Well, it feels the forces, but the X components cancel, and your net force is just in the Y direction. So that's kind of how you would approach a problem like this. I guess this is one thing to note over here I didn't talk too much about, but you can easily make a right triangle out of this shape and solve for what you need. So hopefully that helps. If you had a different problem, assuming the charge is the same, the only thing that would be really different are your distance values and then your basis. So it might not necessarily be in the X or Y direction, or it could be in a combination of both. You know, like I said, if this were moved up here, well, now your force has an X and a Y component. I did not want to do that. I wanted this. Okay, well, either way, that one would also have an X and a Y component. If you were given a different shape outside of a triangle, you'd essentially do the exact same thing. So like if you just had, let's see if I can get it up just to show you. I don't know if you still only have 4 charges, but a good example is you could have one here, and then maybe one here, and maybe one here. So you got maybe minus Q1, we'll just say Q1, Q2, Q3. And maybe right in the center here you'll have Q4. And you'll see something similar where these forces, this one that's pulling it towards Q3, assuming they're opposite charges like in the problem we had, and this one pulling it to Q1 will cancel, and your net force would be just in the direction of Q2, which, depending how you set up your coordinate system, would have an X and a Y component to it. So I kind of apologize a little bit to the guy that asked, because as I was starting this video, I was pulling up my phone to look at the values he gave, and I just realized that it is not exactly, I'm not exactly sure what he means by that. The charges are not in the sum structure. They can be in any place, but we use a triangle for convenience. So I'm not sure if he means like the charges could be moved up and down the triangle, or even, which is what I think he means, you might not even have a triangle. You could have like a square or a rectangle or a circle or something. And for that one, I mean, it would kind of depend on where your charges are, because one thing that impacts your force is the distance between the charges. So somehow we want to relate the distance between the charge we're interested in and the charge that is exerting an electric force on it. So hopefully that kind of helps. I still feel that working through this specific problem will be helpful to see how you would do an example of one, and also for other students who might have a similar problem as this. So if that helps you at all, please like and subscribe, and I will post more videos.